Hey, welcome back to Fat Mama Physics. In this video, we're going to do a quick example. Not really quick. It's broken down into A, B, C, D questions. And it is on uniform electric fields between two charged plates. Notice we have here a proton. We're just going to put it on one end of the plate and see how it's going to accelerate to the other end. So, let's begin. All right. Here we have a two-plate. The first question, what is the magnitude and direction of the electric field? First of all, we know the electric field here is uniform, okay? And because it is uniform, we can basically just say that the potential difference across these plates is going to determine how much electric field is between these two plates. The larger potential difference, the greater the electric field. Also, the difference of separation. So if these plates are separated very much closely, imagine that's going to generate a whole that's a really high electric field in between versus if it were further apart. So if you kind of think about as slope elevation, if 2 points on, let's say if you want to climb 100 meters, if you say you want to climb 100 meters with, say, a very steep slope, then the difference in elevation between 0 meters and 100 meters, that distance between these two is going to be very narrow, just like how the separation of the plates are very narrow between two different potentials. And of course, if you say, another analogy is if you take a ladder. If you want a steeper ladder, you just have to squeeze it in tighter against the wall. If you want a more kind of easier climb on your ladder, then you can have it spread out a little bit further, assuming you allow that. But of course, the ladder the ladder can't extend, so you'll probably affect the height you're able to achieve. But let's say that you have an extendable ladder, then that means you have a less steep slope to climb, meaning that you have a smaller electric field between the two elevations. Okay, so the relationship here, hopefully you have seen this one before, is the electric field imagine it's like the gradient of your electric potential change over space, or the distance of separation. So that's the delta V, which is the potential difference across the spacing, divided by the spacing. So the potential difference, this very wonky pen here. Okay, so the potential difference between 400 and negative 400, of course, you take the difference, that's going to be 800 in total. So that's 800 potential difference across the two plates, divided by the distance of separation, 0.025 meters. If it's in centimeters, you would have to convert it to meters. So after you divide the two, I put this in my calculator, 0.025, this gives me 32,000. So that's 32,000. And units, you can use a volt per meter, or you can use Newton per Coulomb. These two units both work. And the Newton per Coulomb units is based off of the core definition of what an electric field is. The amount of newtons used, the amount of electric force acting on a single charged particle on a unit charge. So that's Newton per Coulomb, okay? So, hey, guess what? We're going to use that definition. I think I put the units in that way, so it kind of gives you a hint of what to do next. So the next question is, now that we know the electric field between these two plates, how much electrostatic force would a proton experience? And that has to come from the definition of what an electric field is. The electric field is essentially the amount of electrostatic force acting per unit of charge, or by reference, a positive charge. Hey, it's a proton, so perfect. Okay, so if we rearrange this one for the amount of force experienced on the proton, then that's going to give us EF is going to be equal to EQ, meaning the larger the electric field, the greater the force acting on the proton. The larger the charge on the proton, also the larger force will be acting on the proton. So since we know the electric field, we know that a proton is essentially just an elementary charge, we can go ahead and substitute these in. So that's 32,000 Newton per Coulomb times the elementary charge 1.6 times 10 to the negative 19 coulombs here. And we just multiply to give us 1.52, and 1.52 times 10 to the power negative 15 newtons, and rounded up to 2 sig figs will give us exactly that. Okay? All right, hey, we're just moving pretty good here. C, what is the velocity of the proton when it exits the other plate? So it's going to be exiting this other plate, and this notation here looks really funny, but all of it, what that means is it's trying to say there's 3 significant figures there. The 2 zeros are significant digits. So what we should need to do is we need to see how much kinetic energy this proton is going to be able to gain on the other side of the plate. So essentially, assuming that no other energy is lost, notice you're thinking, whoa, you went from Newton's second law and all the way to energy. So that's kind of the essence. You kind of have to be able to work very freely amongst all the different classical mechanics concepts. So here, when we talk about exiting, you're probably thinking, oh, could I use a kinematics equation for this one? Yeah, you totally could. And that's a connection between kinematics and energy as well. But energy is just so much easier because energy, I don't have to worry about the path taken. I just have to worry about the initial and the final points. So as long as there's no energy lost, which there shouldn't be in this case, then I just have to worry about how much potential energy this proton has here. It's going to convert all of that electric potential energy into kinetic energy when it exits the hole on the other side. So what I want to do is essentially, I just need to find the electric potential there, or the amount of work the amount of work I have to do to move this proton from this side of the plate to the other side of the plate. So many ways you can think about it, but the easiest way to think about that is we know that the amount of work, or the amount of energy, since work is energy, the amount of energy we're going to get from this electron going through a certain potential difference is proportional to the difference in the electric potential times the charge. So this also came from a definition, which is the electric potential difference that between 2 points is equivalent to the amount of work done per unit of charge of moving that charged particle from point A to point B. So rearranging this definition gives us this one over here, which is going to give us the amount, this is going to be opposite way. This is not the work done to move him there. Now if I release that particle there, it's going to have all the potential energy, which it will convert it to kinetic energy. So this amount of work, a delta VQ, I will use for my potential energy here. So here I'm going to get the potential difference times the charge, which is going to be the amount of work done, or the potential energy. This is going to be equal to my kinetic energy. We know kinetic energy is 1/2 mv squared. So I'm going to substitute that right in here, which is 1/2 mv squared. This delta VQ here, this is the EP, don't forget that. The amount of potential energy that will be released or will be converted to the kinetic energy over here. Okay? Awesome. So now we can solve for the velocity. We can do this by, say, me multiplying this 2 up over here. Okay. This is just algebra, essentially. I get 2 delta VQ and is equal to mv squared. So I just move the m over. Okay. You know what, if you want to skip all this annoying part, feel free to do that if I'm just doing the algebra. Last but not least, I take the square root of both sides to get rid of the v squared. So finally, I get v is equal to the square root of 2 times the delta v, which is the potential difference, times the charge of this proton divided by the mass. Okay, so I will put it in. I get 2, and this is going to be 800 volts total, times the elementary charge, which is 1.6 times 10 to the power negative 19 for a proton, divided by the mass of a proton. You can find in your data booklet or IB data booklet, whichever one you're using. I believe it's 1.67 something times 10 to the power negative 27. It's going to be close enough to what I need to get. So putting that in, I get 931527, which is going to round up to 391,527. Oh, sorry, 390,000 meters per second. And you know what? I probably used the wrong value. It's not, maybe 1.66 something, but anyways, close enough. Anyways, there's the speed of my proton when it exits the other side. Last but not least, how much work is needed to move this proton at constant speed from the negative plate back to the middle of the two plates? Ooh, it's back to the middle of the two plates. Okay, so it's not all the way back to the other plate. So we know that, again, the amount of work done is on acting on a proton to move it from one place to another is going to depend on the difference in electric potential times the charge on the proton. And in this case, since we're only moving it back to the middle, if we're moving it back to the middle, we know the middle is exactly 0 volts. So the potential difference is going to be 400 only. 400 volts only. So this is why I'm going to use 400 volts times the elementary charge, which is the charge on the proton. And this is going to hopefully give me, I get 6.4 times 10 to the power negative 17. So that is how much energy that needs to be done. Oh, hey, look at these units. Ha ha ha. There's a mistake in the units. Is in joules, because we're talking about work. So there you go. That's it. That's this question. So I would say this is a very standard, typical multi-part question when we talk about a constant electric field. So be very careful. This equation here, where you look at the gradient for the electric field, you cannot use this unless the electric field is constant between two plates. Unless you're into calculus and you can see, basically you can do a differential equation using a using a derivative to find exactly the electric field at a specific spot. You cannot use this one, say, for a charged particle and finding, say, the electric field between 2 points, because the change in the potential difference is not going to be uniform, not like this case. So be very careful when you can use this one. Typically, the examples you'll see will mostly be will be on charge plates. So please be careful of that. Otherwise, this is your typical question. Thank you for tuning in, and hopefully you learned something that will help you with your practices. Next video, I'm going to do this challenge, Millikan oil drop experiment. Thank you for watching. Van Mama Physics signing out.